Hello everyone, I Madhuri Gupta, Assistant Professor, Department of Computer Science and Engineering, Chhattisgarh Swami Vivekanand Technical University, Bhilai. Welcome you all to our lecture on state space search, a cornerstone technique in the realm of artificial intelligence. Over the next 30 minutes, we will journey through the intricacies of state space search, exploring its principles, applications and real world significance. Before that, let us have a quick recap of our previous lecture on Introduction to AI. Artificial intelligence or AI is the study of creating computer system that can perform tasks that typically require human intelligence. It involves perceptions, reasoning and decision making capabilities. AI encompasses various areas such as search, machine learning, computer vision, natural language processing, knowledge representation, expert system and more. AI finds application in diverse fields like healthcare, finance, gaming, autonomous vehicles and virtual assistants. It's revolutionizing industries and improving our lives. The history of AI dates back to the 1950s when researchers first coined the term. Since then, AI has witnessed significant advancements and breakthroughs. The Turing test proposed by Alan Turing assesses a machine's ability to exhibit intelligent behavior unmatchable from that of a human. In summary, artificial intelligence has evolved into a powerful technology that holds immense potential to shape our future. From search algorithm to self-driving cars, AI is changing the world we live in. In the fascinating world of artificial intelligence, one powerful concept stands out: search. Search can be applied to solve a wide range of problems, each with its unique challenges and solutions. Let's begin with the fundamentals. State space search is a problem solving strategy that enables AI systems to navigate through a problem's solution space. It involves exploring different states of the problem to find the optimal solution. Imagine you are planning a road trip. You want to find the shortest path on a map to reach your destination efficiently. AI powered search algorithms can quickly calculate the optimal route, guiding you through the maze of roads and highways. The state space search is a fundamental concept in artificial intelligence, representing the set of possible states that we can reach in a problem by applying specific operators to a starting state. How to control the search? An initial state where the problem starts. A state of operators means actions the agent can take. A set of goals where the problem ends. A path cost function which determines how much cost that node contains. Measuring effectiveness. The total cost in the sum of search costs and the path cost which may not be real. The toy problem versus real world problem. Most of the problem we will work on will be toy problem, like puzzle problem, 8 puzzle problem, 15 puzzle problems, 8 quints problem, water jug problems, crypt arithmetic, the real problems. But in fact, these techniques are used to solve real problems like route finding in airline travel planners, traveling salesman problems, planning drill movements for automatic circuit board drills, VLSI layout, cell layout and channel routing, automatic manufacturing, assembling sequencing. Now, we come to the point where we can know the steps in state space search. Here are the state space flow chart. So, first we will start with the initialization state, then we will go with the current state, then if the goal is the start state, then we will end with the goal state and we will terminate our search. Otherwise, we will explore all the successors of that points, and if the search is found then we will go with the stop state, otherwise we will repeat all the steps once again. So, state space representation. State space representation involves defining an initial state and a goal state and then determining a sequence of actions called states to follow. In this diagram, we have state, space, search, search tree and transition model, where state represent the current state, initial state and the goal state. Space means the area where the problem can be solved, like in the 8 puzzle problem we have 3 by 3 of matrix, and the next is search, means which technique we have to follow, like breadth first search or depth first search, and by this we have search tree which explore the tree diagram of our search, and here in transition model where we have to represent from where the state goes from initial state to current state to the goal state and how the cost will incorporate with each node. This is the flow of state space search. Now, we come to the point where we can explore one of the example. So, we have to go through with this 8 puzzle problem. Here in this diagram you can see one is the initial state and one is the goal state. Here we have 3 by 3 grid where initial state representing 7, 2, 4, 5, 0, 6, 8, 3, 1 and the goal state start from 0, 1, 2, 3, 4, 5, 6, 7, 8. Let us take this example and consider a puzzle where we have 3 by 3 grid with 8 numbered tiles and 1 empty space. The goal is to arrange the tiles in a specific order. Each move in this puzzle can shift a tile into the empty space. A problem consists of an initial state which can be represented by theta 0, a list of possible actions that represent by alpha for the agent, a goal and a path cost. One way to solve this is to search for a path. So, from theta 0 to theta 1 to theta 2 up to theta n, such that theta n is a goal state. So, here we have examples of 8 puzzle where we have 2 examples where 2 tiles representation you can see. First, initial state representing 7, 2, 4, 5, 0, 6, 8, 3, 1. In the final state or in the goal state we have 1, 2, 3, 4, 5, 6, 7, 8. And in another example we have 2, 8, 3, 1, 5, 4, 7, 0, 5 and we have goal state like 1, 2, 3, 8, 0, 4, 7, 6, 5. So, state means specification of each of the 8 tiles in the 9 squares. The blank is in the remaining square. The initial state means the any state. Successor function, that means action. Blank moves left, right, up or down. Goal test, check whether the goal state has been reached. Path cost, each move cost 1. The path cost is equal to number of moves. Here we have 2 figures, figure A representing different arrangement of 8 puzzle problem where we have different initial state and we have different goal state, and in the second figure we have different initial state and we have different goal state. Examples, theta, that means all the states 7, 2, 4, 5, 0, 6, 8, 3, 1 and the another theta is equal to 2, 8, 3, 1, 6, 4, 7, 0, 5. So, we have successors of our problem which define how we can move our tiles from up, down, right or left. So, how we can explore each of our tiles. In this figure we have different arrangement. If we go with the left tiles, what will be the result, and we will go with the down arrow, then what will be the tiles, and if we go with the right flow, then what will be the your arrangement of your initial state or the current state. Application of state space search. State space search algorithm are used in various fields like robotics, game playing, computer networks, operations research, bioinformatics, cryptography, supply chain management. Search. Search is the systematic examination of states to find path from start or root state to the goal state. Search usually results from a lack of knowledge. Search explores knowledge alternatives to arrive at the best answer. Search algorithm output is a solution, that is a path from the initial state to a state that satisfied the goal state. Examples for a robot: this might consist of pick up, put down, move forward, move back, move left and move right until the goal is reached. Puzzles and games have explicit rules. For example, the Tower of Hanoi puzzle. We have Tower of Hanoi where we have initial state and we have goal state. This puzzle involves a set of rings of different sizes that can be placed on 3 different pegs. The puzzle starts with the rings arranged as shown in the figure A. The goal of this puzzle is to move them all as to figure B. Condition: only the top ring on a peg can be moved and it may only be placed on a smaller ring or on an empty peg. In this Tower of Hanoi, a situation encountered while solving the problem are described as states. Set of all possible configuration of rings on a peg is called problem space. State means a state is a representation of element in a given moment. A problem is defined by its elements and their relations. Problem solution: in the state space, a solution is a path from the initial state to a goal state or sometimes just a goal state. A solution cost function assigns a numeric cost to each path. It also gives the cost of applying the operators to the states. A solution quality is measured by the path cost function, and an optimal solution has the lowest path cost amongst all solutions. The solutions can be any or optimal or all. The importance of cost depends on the problem and the type of solution asked. Problem characteristics: decomposability of the problem into a set of independent smaller subproblems. Possibilities of undoing solution steps if they are found to be unwise. Predictability of the problem universe. Possibility of obtaining an obvious solution to a problem without comparison of all other possible solutions. Type of the solution, where it is state or a path to the goal state. Role of knowledge in problem solving. Nature of solution process with or without interacting with the user. Problem decomposition. Here we have one example where we have to integrate x to the power 3 plus x square plus 2x plus 3 sin x dx. So, we can divide the problem into sub problems. First we have to solve x to the power 3 dx. The solution will be x to the power 4 by 4. Then we will solve x square dx. The solution will be x to the power 3 divided by 3. Then we have to solve integration of 2x dx. The solution will be 2x dx, and then finally we will get x to the power 2. And then next we have to integrate 3 sin x dx, then the solution will be 3 sin x dx, then finally we will get minus 3 cos x. This problem can be solved by breaking it into smaller problems, each of which we can solve by using a small collection of specific rules. Using this technique of problem decomposition, we can solve very large problem very easily. This can be considered as an intelligent behavior. Can solution steps be ignored? First, ignorable, in which solution step can be ignored. For example, theorem proving. Second, recoverable, in which solution step can be undone. For example, 8 puzzle. Third, irrecoverable, in which solution steps cannot be undone. For example, chess. Characteristics of production systems. Production systems provide us with good ways of describing the operations that can be performed in search for a solution to a problem. We have categories of production systems. We have monotonic production system and we have non-monotonic production system, and we have partially commutative and we have non-partially commutative production system. In monotonic system, we can involve theorem proving. In non-partially commutative, we can include chemical synthesis, and in non-monotonic, we can involve in partially commutative way, we can involve robot navigation, and in non-partially commutative, we can involve bridge. Now, it is time to check your understanding. Here is one question: what is state space search? Option A, a technique to solve a problem by searching through a set of possible states. Option B, a technique to solve a problem by guessing the answer. Option C, a technique to solve a problem by randomly trying different solutions, and option D, none of the above. So, think about it, and here is the right answer, the option A, that means a technique to solve a problem by searching through a set of possible states. So, now we have come to the conclusion. So, state space search is a problem solving technique using in AI to find a solution to a problem by exploring all possible states of the problem. It is an exhaustive, complete and optimal search process that can be classified as uninformed or informed search. State space representation is a crucial step in the state space search process, as it determines the efficiency of the search algorithms. State space search in artificial intelligence has several applications, including game playing algorithms, natural language processing, robotics, planning, scheduling and computer vision. Thank you.